Welcome back to the MongoDB Schema Design Anti-Patterns video series. This is part 2 in the series. If you missed part 1, I recommend you watch part 1 and then return back here. In the first video in this series, we talked about the massive arrays anti-pattern and the massive number of collections anti-pattern. Today, we're going to cover the next 3. I'll discuss unnecessary indexes, bloated documents, and case-insensitive queries without case-insensitive indexes. Let's begin with the unnecessary indexes anti-pattern. Now, indexes are great, seriously, but it's easy to get carried away and make indexes that you'll never actually use. So let's examine why an index may be unnecessary and what the consequences of keeping it around are. So before I go any further, I want to emphasize that indexes are good. Indexes allow MongoDB to efficiently query data. If a query does not have an index to support it, MongoDB performs a collection scan, meaning that it scans every document in a collection. Collection scans can be very slow. If you frequently execute a query, make sure you have an index to support it. So now that you have an understanding that indexes are good, you might be wondering, should I just create an index on every field, just in case I'll need it in the future? The answer to that is a big no. There are 3 big reasons why you should remove unnecessary indexes. Well, first up, indexes take up space. Each index is at least 8 kilobytes and grows with the number of documents associated with it. Thousands of indexes can begin to drain resources. Indexes can impact the storage engine's performance. So as I discussed previously while explaining the massive number of collections anti-pattern, the Wired Tiger storage engine stores a file for each collection and a file for each index. Wired Tiger will open all files upon startup, so performance will decrease when an excessive number of collections and indexes exist. Indexes can impact write performance. Whenever a document is created, updated, or deleted, any index associated with that document must also be updated. These updates to the indexes negatively impact write performance. In general, we recommend limiting each collection to a maximum of 50 indexes. So what you want to do is identify which indexes are truly necessary. So how do you know if an index is necessary? Well, unnecessary indexes typically fall into one of 2 categories. First, the index is rarely or not at all used. Or second, the index is redundant because another compound index covers it. Let's take a look at an example. Leslie often looks to other powerful women for inspiration. Let's say Leslie wants to inspire others, so she creates a website about her favorite inspirational women. The website allows users to search by full name, last name, or hobby. Now, Leslie rhetorically asks if she's going to make her website awesome. You know she will, because she's Leslie. Let's take a look at how Leslie modeled her data for this awesome website. Let me go ahead and jump over to Atlas. So let's say Leslie used Atlas to create her database. She created a collection named Inspirational Women. Inside of that collection, she created a document for each inspirational woman. So here we can see a document for Sally Ride. Let's take a look at the indexes Leslie created. Now, it looks like Leslie must have gotten on a sugar high from eating way too many Nutrium bars. And she created an index for every field in the collection. Now, let's see if those indexes are really necessary. It looks like only 2 indexes are being used frequently. Her compound index named last name 1, first name 1, and her index named hobbies 1. Let's think about why the other indexes are not being used. If someone searches by full name, the query will use the last name 1, first name 1 index. If someone searches just by last name, the query can also use the last name 1, first name 1 index. Both searches are covered by the same index. The last name index is redundant, so it can be dropped. Searches for inspirational women by hobby are covered by the Hobbies 1 index. All of the other indexes are unnecessary as they aren't actually being used. So Leslie could choose to drop them by clicking Drop Index. In addition to using the Data Explorer, you also have the option of using MongoDB Compass to check for unnecessary indexes. I'm in the Indexes pane for her collection. Just like we did in Atlas, we can see that the last name one, first name one, and the Hobbies 1 indexes are being used regularly. Now, just as we could in the Atlas Data Explorer, we have the option of dropping the unnecessary indexes. So let's summarize this unnecessary indexes anti-pattern. Do create indexes that support frequently run queries. Remember that indexes increase read query performance. Don't create unnecessary indexes. Unnecessary indexes reduce performance and take up space. An index is considered to be unnecessary if it's not frequently used by query or it's redundant because another compound index covers it. You can use the Atlas Data Explorer or MongoDB Compass to help you discover how frequently your indexes are being used. When you discover an index is unnecessary, remove it. All right, we've made it through the first half of our anti-patterns. Let's move on to our next anti-pattern, bloated documents. Here's the thing. You don't want to feel bloated, and you don't want your documents to be bloated either. Let's dig into what I mean by that. You've already heard me say this at least once, but I'm going to repeat it now. Data that is accessed together should be stored together. Note that it doesn't say data that is related to each other should be stored together. Sometimes data that is related to each other isn't actually accessed together. You might have large bloated documents that contain information that is related, but not actually accessed together frequently. In that case, separate the information into smaller documents in separate collections and use references to connect these documents together. So you might be wondering, if MongoDB has a 16 megabyte document size limit, who cares if my documents are bloated as long as they are smaller than the document size limit? To answer that, we need to get into some of the details of how data is stored in MongoDB. WiredTiger is the default storage engine for MongoDB. WiredTiger stores all of the indexes and documents on disk. At a high level, WiredTiger also keeps all of the indexes, plus the documents that are accessed the most frequently, in something called the WiredTiger cache. The cache is stored in memory. One important term to know is the working set. The working set is the data that MongoDB uses most often. You can think of it as the data that your application uses on a regular basis. When the working set fits in the WiredTiger cache, MongoDB can query from the cache, which is really fast. When the working set does not fit entirely in the cache, MongoDB will need to pull some of the documents from disk. Pulling documents from disk is slower than pulling from the cache, so it's ideal to have the working set fit in the cache. One way to reduce the size of the working set is to ensure that the most recent regularly accessed documents only contain information that is frequently needed by the application. Essentially, you want to remove the bloat from your frequently accessed documents. You have to do a little math to figure out how much space is in the WiredTiger cache. So the cache is the larger of two numbers, either 50% of the total RAM available minus 1 gigabyte or 256 megabytes. If that's fuzzy, don't worry, let's work through an example. Let's revisit Leslie's website for inspirational women that we discussed in the previous anti-pattern. Leslie updates the homepage to display a list of the names of 100 randomly selected inspirational women. Let's say a user clicks on Sally Ride. They'll be taken to a new page with all of the detailed biographical information about Sally. Leslie gets to work and fills the website with information about 4,704 inspirational women, including herself. Leslie jokes that she is big enough to admit that she is often inspired by herself. Let's take a look at how Leslie has modeled her data. Leslie has created a collection named Inspirational Women. Inside of that collection, she has created one document for each woman. Here's her document for Sally Ride. Leslie is able to easily get the data she needs on her website, but she notices her homepage is lagging a bit. The homepage is the most visited page on her site, and if the page doesn't load quickly enough, visitors will abandon her site completely. Now, Leslie is using an M10 dedicated cluster. Let's take a look at the config. As you can see, with an M10, you get 2 gigabytes of RAM. Let's do some calculations to determine how big her working set is. We know that the size of the WireTiger cache is going to be the larger of these two numbers. So for an M10, let's calculate that first bullet. We know an M10 has 2 gigabytes of RAM. So starting inside those parentheses, 2 gigabytes minus 1 gigabyte is 1 gigabyte. Now 50% of 1 gigabyte is 0.5 gigabytes. So 0.5 gigabytes is greater than 256 megabytes. So we know the WireTiger cache is half a gigabyte. So how do we know if our working set will fit in the cache? Let's head back to the Data Explorer. Here we can see that the Inspirational Woman collection is 580.29 megabytes. Her index size is 196 kilobytes. When we add those two numbers together, we get roughly 0.58 gigabytes, which is larger than 0.5 gigabytes. So we've exceeded the size of the WireTiger cache. So we've got two choices. We can move up from an M10 to an M20 dedicated cluster, which will give us more RAM. Or we can restructure our data in order to get our working set into the RAM allotment. Both are good options. Moving to an M20 is a pretty easy process. The cluster just costs a little more. Let's walk through how we could restructure our data. We want to optimize for our use case, so let's take another look at the website. The query on Leslie's homepage only needs to retrieve each woman's first name and last name. Having this information in the working set is crucial. The other information about each woman, including a lengthy bio, doesn't necessarily need to be in the working set. Leslie can break up the information in her Inspirational Women collection to better match her use case. Let's take a look. Leslie can split her data between two collections, Inspirational Women Summary and Inspirational Women Details. The homepage will query the Inspirational Women Summary collection. Let's take a look at a document in the collection. As you can see, the document has fields for ID, first name, last name, and Inspirational Women ID. That Inspirational Women ID is a manual reference to the ID of a document in the Inspirational Women Details collection. Here we can see all of the information that the web page that displays details about each woman will need. Now let's see if this data restructure fixes our working set problem. Here we can see that the total index size for both collections is 312 kilobytes. We can also see that the size of the Inspirational Women Summary collection is about 455 kilobytes. If we add 312 and 455, we get 767 kilobytes. Now 767 kilobytes is significantly less than the half gigabyte dedicated to the WireTiger cache. Because of this, many of the most popular documents from the Inspirational Women Details collection will also fit in the cache, which is great. Now, some of you might be concerned that we duplicated data in this solution. Isn't data duplication bad? Well, historically, data duplication has been frowned upon due to space constraints, as well as the challenges of keeping the data updated in both collections. Now, storage is relatively cheap, so we don't necessarily need to worry about that here. Additionally, the data that we've duplicated is unlikely to change very often. In most cases, you won't need to duplicate all of the information in more than one collection. You'll be able to store some of the information in one collection and the rest of the information in the other. It really all depends on your use case and how you are going to use the data. So let's summarize the bloated documents anti-pattern. Do store data together that is accessed together. Don't bloat your documents with related data that isn't actually accessed together. Be sure that the indexes and the most frequently used documents fit in the WireTiger cache for your database in order to get blazing fast queries. All right, let's move on to our fifth anti-pattern, case-insensitive queries without case-insensitive indexes. Just to make sure we're all on the same page, when I'm talking about a case-insensitive query, I'm talking about querying for a string, and I don't care about matching on the letter case. For example, if I'm querying for the word dog, I don't care if it's stored in the database with a capital D or with a lowercase d, or if someone did something ridiculous and spelled it with a capital O in the middle. I want all of those results to be returned. That is a case-insensitive query. Now, not having a case-insensitive index can create surprising query results or slow queries and make you hate everything. Now, the good news is, once you know the details of how case-insensitive queries work, the implementation is fairly simple. So let's dive in. So how can you get into trouble here? Well, there are two big ways. Regex queries with the I option will give you the case-insensitive results, meaning that you'll get all of the results back that match regardless of the letter case. Unfortunately, regex cannot efficiently utilize case-insensitive indexes, so these queries can be very slow, depending on how much data is in your collection. The other way you can get into trouble is non-regex queries. Now I'm talking about regular queries where you just search for a match. These queries that are not supported by a case-insensitive index will return case-sensitive results. Let me say that another way. For non-regex queries, you must have a case-insensitive index if you want case-insensitive results. So before we jump into the example, I want to define one term we'll be using. Let's talk about collation. A collation defines the language-specific rules that MongoDB will use for string comparison. Collations have various properties. One of these properties is a strength that ranges from 1 to 5. The strength defines the level of comparison to perform. Collation strengths of 1 and 2 both give you case insensitivity. Indexes can have collations. A query that is run with the same collation as a case-insensitive index, remember, that means it has a strength of 1 or 2, will return case-insensitive results. Let's take a look at an example so you can see what I mean. Let's continue on with Leslie's database of inspirational women. It currently has over 4,700 inspirational women. It includes records for both Harriet Tubman and Harriet Beecher Stowe. So let's try to find them. So I'm going to search for first name equal to Harriet. Let's check that out. Okay, so that's not great. We're not getting the results back for Harriet Beecher Stowe. Let's head over to the explain plan and investigate. So we can see that the winning plan is using an index scan with the first name 1 index. In the execution stats, we can see that only one index key was examined and only one document was examined. Now this was a very fast query because it's efficiently using an index, but it's not giving us the results we want. We want all of the Harriets, regardless of what letter case is used, to be returned. Let's try another query. This time, let's use regex with the I option. So what I'm going to do is come over and say where first name is equal to, we'll say $regex, and here we'll say /Harriet with the I option. And remember, /I is what's giving us that case insensitivity. All right, now we're in business. Now we have both Harriets. Let's check out the explain plan. This query, just like the last one, uses an index. However, since regex queries cannot efficiently utilize case-insensitive indexes, we are not getting the typical benefits of a query that is covered by an index. All 4,704 index keys are being examined as part of this query, resulting in a slightly slower query than one that fully utilizes an index. So we're getting the results we want, but the query is not as fast as it could be. Let's try to get the best of both worlds. Let's create a new case-insensitive index. So let's name this index first name case-insensitive. Let's create the index on the first name field. Set the order to ascending. Now what we want to do is use a custom collation. So I'm going to set the locale to English. And I'm going to set the strength to 2. Now remember that the strength needs to be set to 1 or 2 in order to get case-insensitive results. So I'll click Create Index. Let's head back to the Documents tab and search again for Harriet. Okay, still only one Harriet. Okay, why is that? Well, that's because the collation of our query didn't match our index. So let's fix that. I'm going to pop open this options pane, and I'm going to set the collation to match that index we just created. So I'll say locale is equal to English, and the strength is set to 2. And let's run that query again. Hey, now we've got both Harriets. So let's check out the explain plan. Here we can see that the winning plan is executing an index scan that uses the case-insensitive index I just created. 2 index keys are being examined and 2 documents are being examined. Now this query is executing in 0 milliseconds. That's pretty fast. We saw that we were able to get the correct case-insensitive results we expected extremely fast by creating a case-insensitive index and running a query that was supported by it. I want to show you one more way to achieve the same result. When you create a collection, you have the option of setting a default collation that all queries and indexes will use by default. So let me open up my database named Favorite Things. Inside of this database is the Inspirational Women collection we've been working with. I've created another collection inside of this database that has the same documents. The only difference is that when I created the collection, I set the default collation. As you can see, I set the locale to English and I set the strength to 2. So by default now, all of the queries and indexes in this collection will use that same collation. Let's create an index on the first name field. So I'll select first name, set the order to ascending. Now I don't have to set the custom collation here because it's set by default, so I'll just click Create Index. Let's run a query to search for Harriets. So I'll say where first name is equal to Harriet, and let's run this query. Here we can see we're getting both Harriets. We have case-insensitive results. Let's check out the explain plan. We can see that this query is successfully using the index we just created, so it's executing really quickly. I was able to get case-insensitive results because I set the default collation when I created the collection. Let's summarize the case-insensitive queries without case-insensitive indexes anti-pattern. So you've got 3 primary options when you want to run a case-insensitive query. Do use regex with the I option, but keep in mind this option won't be as performant because regex cannot fully utilize case-insensitive indexes. Do create a case-insensitive index with the collation strength of 1 or 2, and specify that your query uses the same collation. Another option is to set the default collation strength of your collection to 1 or 2 when you create it, and do not specify a different collation in your queries and indexes. So let's summarize what we talked about today. We discussed that indexes are good, but you don't want to create unnecessary indexes. Then we talked about bloated documents. We learned that data that is accessed together should be stored together. If data is related to each other but not actually accessed together, it should not be stored together. And finally, we talked about the importance of having case-insensitive indexes to support case-insensitive queries. All right, be on the lookout for part 3 in this series where I'll discuss the 6th and final anti-pattern. Hope to see you soon.